Hello everyone, I'm going to be your lecturer for today. Yeah.
So I'll give the floor to him. So go introduce yourself a little bit.
Yeah, I actually have a slide to introduce myself
So
after
thank you
this.
so much for
All good. Thank you to Dr. Liu for actually giving me the opportunity to come speak to you guys. So we're going to have a lecture today on statistics and error propagation. I'm a fourth-year nuclear engineer. We'll talk about that on the next slide. And the reason that I want to talk about this stuff, we will also talk about once we start looking at the plan for this lecture. The reading I would recommend you all do if you have the time and the energy is Data Reduction and Error Analysis, as you can see on the screen, by Dr. Bevington. It's a really good book, good pacing, good writing, and a lot of the content from this lecture is inspired or taken from this book. I don't know what lecture number this is, I'm sorry, so you're just going to have to figure that out. So who am I? I'm Ethan Dhami. I'm a fourth-year Bachelor's of Nuclear Engineering student here at Ontario Tech. My pointer is going to be the spatula for today. And I want to talk a bit about why I'm here. So Dr. Liu's brought me in here because we are going to change some of the content in the scientific instrumentation course. Some content was moved to the integrated engineering laboratory, which left a bit of a gap in here, which I was invited to fill. And so we're going to talk a lot more about error analysis, mostly because I got grilled on my error analysis this summer on a paper I wrote, and ever since I have taken a lot of time to put a lot of care into that, and hopefully to prevent you all from getting grilled. And then we're going to talk about electric circuits, and we'll talk a bit more about what sort of electric circuits we're going to be looking at as the year progresses. So I don't know how many guest lectures I'm going to do. I'd say at least 2, this one included. Why you should trust me, GPA above 4.0, not going to specify how much. Is that the only reason you should trust me, or is that a good metric to trust me? No, it's not, actually. Because you'll see here, I was also the president of our student rocketry design team. And I can tell you that I saw people who had GPAs above 4.0 who had no idea what they're doing. I also had people with GPAs around 2 who were some of the best engineers I've ever seen. All GPA really measures is how well you perform as a student in the university setting. Does it speak to your ability as a thinker, an educator, a researcher? Not really, it's just one facet of that. So I actually want to include that just so I could yap about that. The other stuff I've done is I've worked under Dr. Mashrafi and Dr. Liu. And I've done well enough that I've been invited to speak for you all. So I think I'm doing okay there. And just as a disclaimer, I do get ocular migraines. So if I do have to stop lecture for that, I will try and pick up and have a half lecture or something. Fingers crossed doesn't happen though, because I would have a bad day myself. And that's actually me in BC. I'm from Vancouver. That's Lake Okanagan. Don't know if any of you have ever heard of the Ogopogo. That's where he lives. So let's get into the lecture. And what I want to start off with is actually a pre-lecture question. Dr. Akita likes to do this, and I figure I'd be a fan of it too. So if you all want to take some time to guess, and please don't use a calculator, because we're going to go through this, because you don't actually need a calculator to figure this one out. What do you guys think is greater? Euler's to the power of pi or pi to the powers of Euler? It's a actually fairly common question asked in math circles. But do you have any idea of how you would go about showing this, or what do you guys think is the greater value? Does anyone want to make a guess here? Ivan? Limits first, okay. So we could use limits, that's one thing. One proof that I've seen people try uses limits, and then they set up like a subtraction or a division, and they use L'Hopital's. The issue is they use L'Hopital's incorrectly, because these are real values. They'll have like Euler's to the pi divided by pi to the Euler's, and what ends up happening is they go, we're going to apply L'Hopital's to this, and we're going to see what it evaluates to try and get the powers down. L'Hopital's only works for indeterminate cases. These are very determinate numbers. So that's, you could, and I don't know if we do, but I have the proof in here, so let's get started. Now, don't lie to yourself if you got the answer wrong, it's okay, because I'm actually going to make a bad guess. to start off this proof. And the way we're going to start off this proof is to make an assumption. You'll notice in a lot of proofs, it's a lot easier if you take a stance. It doesn't matter if it's right, doesn't matter if it's wrong, just take a stance. So we're going to assume that pi to the power of Euler's number is greater than Euler's to the power of pi. And if this is true, then we can move forward and we can apply the logarithm of base e to both sides. And using our ln rules, we can bring those powers down. Log natural of Euler's number is in fact 1. So if we, I'll grab my spatula here. If we just evaluate this to be 1, take this Euler's number and bring it down to the other side, we actually get a very nice condition that we can work with, which is that we need to show, for this to be true, that pi over Euler's is less than ln to the power of pi. Now, the lovely thing about this, about working with an inequality, is that we can use approximations. And one of the approximations we will use here, so yeah, if this is true, our original assumption is true, the approximation we're going to use is the derivative of ln x, which is somehow, thank you Desmos for this graph, always greater than the actual function of ln to the x. So we can get an inequality from this. So we're going to take some time to look at this one here. So what I'm saying is ln of any value plus an offset is less than the value of the line with that offset. Now it's equal at x when c is 0. But if we move forward or if we move backwards, you can see that our green line here, which is the derivative approximation, is always greater than the red line. So this is a valid thing to say. It's a bit hand-wavy just to show it, but I don't really care because it's quick. So what we're going to do next is we want to get some numbers that we can work with into this. And in fact, we're going to say x plus c is pi, I believe, and x is Euler's number. You can actually see that on the plot I have here, which means that c is going to be pi minus Euler's. So I assume you've all taken calculus. You know what the derivative of ln is. It's 1 over x. So that's where the over e comes from in this term. The pi minus Euler's comes from the c term, which is what it is once we plug in x plus c equals pi and x equals Euler's number. And then ln x, which is our mx plus b term. So that's the b term to ln x. That just becomes log natural of Euler's number. Now the lovely thing is that this guy equals 1. And if it's 1, we can rewrite that as Euler's number over Euler's number. When we add Euler's number over Euler's number to this guy here, that subtraction of Euler's number disappears. So what are we actually left with? A value that we would very much like, which says that ln pi is in fact actually less than pi over e. How do we relate this to our original statement here? Well, this actually contradicts what we said would need to be true for our assumption to be true. I believe this is what we needed, and this is what we got. So what does that mean if we contradicted ourselves? It means we're wrong. It means our assumption wasn't true. And that means that if this is not the case, the other thing must be correct. In fact, if you looked using a calculator, they're very close numbers. It's actually very difficult. But you didn't actually need any calculator to show that this is true. Now, to go on a little side tangent here, if you generalize this problem, please don't be scared from this plot. We're going to look at number pairs. So for example, we're going to look at 1 to 4. So 1 and 4, and then 1 and 4 here. So this is x to the power of y, and which is greater when the red pair is the lesser of the two. So you can actually see that there's an intersection point. We have 4 distinct regions, and the region above the y equals x line flips to be greater of the pairs. It's a weird plot. And then we have this interesting sloped curve, which is the parametric equation y to the x equals x to the y. Of course, this intersection point is very interestingly at Euler's number for x and y. If anyone can tell me why, I don't know, maybe I'll talk to Dr. Liu about giving you bonus points. So that was the pre-lecture question. Hopefully it was in some degree stimulating. But we have to actually get into the content now. So we're going to talk Very first, about degrees of freedom. A lot of the statistics courses I've seen don't actually start with degrees of freedom, which I think is a mistake. Then we're going to talk about the mean and standard deviation, and not just, oh, here it is, review from stats. No, we're going to actually talk a bit about why standard deviation and the mean look the way they look in their formulations. Then we're going to talk about variance and really why standard deviation looks the way it does. We're then going to introduce covariance. We're going to look at sample and population statistics and why it's important to know the difference. Then we're going to have a question break. And hopefully at that point we can go back to anything that might still be unclear. We can clarify all that before we move on to the thing that you might all not like, and you might accuse me of just wanting to cause you all pain and suffering, which is the multivariate Taylor series expansion, which you will not be tested on, you will not need to know. But I will introduce it because it is required to show where the general error propagation formula comes from, which I believe Dr. Liu has introduced. The sigma is the square root of the differential sigma squared plus, yeah, I'm seeing some nodding heads, that's good. And then we'll do an example that's actually very similar to the midterm question that I wrote for you all. So I would highly recommend you all pay attention for that. All right, so very first thing that we're going to talk about here is degrees of freedom. I have my definition of a degree of freedom up here, but does anyone have a definition that does not align with this that they would like to share? There's no wrong answers. This is just a discussion. Okay, good. I guess we're all on the same page. So the way I see degrees of freedoms, and that I think you guys should see them as, is in a system of equations context. Let's look at this guy here. We have how many unknowns? We have two unknowns. How many equations do we have? Just one. Does this mean we can solve for unknowns in any right? And the answer is no. No, we can't. Because there's not enough equations to nail down both of these values. Little disclaimer on saying -1 degrees of freedom. Don't actually ever say that, because it's just, you can't have negative degrees of freedom. But I put it up there to illustrate the point in its relation to the system of equations. Now here we have this one. Two equations, two unknowns. We can solve this. We've done this in first year. This is linear algebra. What we call this is a consistent system. No matter what we do, the answer will be the same. It's consistent. It is consistently the same. Now the big issue happens when you have too many equations and too few unknowns. Because you can figure out what x1 and x2 are. And they can be a couple things, and that's the big issue. You can say there's something, and it's true, but it's also not true at the same time. And so when we have this, we call that a degree of freedom. The values have freedom to not be nailed down, but to still be determined. So where do we see degrees of freedom in the wild? Does anyone have any idea where you would see a lot of degrees of freedom? And the hint is in this course, in the course's content. Okay, I'll give you the answer then. It's statistics and measurement. And why? Well, it's because when we measure, I put length of a rod, for example, but I'm not even going to talk about what I wrote for word. But when you measure anything, let's say the spatula, for example, I want to measure the length of the spatula. I could put some big calipers from here to this tip, or to the middle here, or to here, or I could try and measure the straight length or whatever. But either way, there's a lot of ways that this measurement could be different. And that's because it's not a perfect object. There's not a single value that could describe the length of this spatula. That's why we get so many different values. So how do we deal with these values? Are we going to just provide a big list to somebody who asks, what's the length of your spatula? No, because then they'd tell you, what are you doing? Get out of here. Do better. In fact, what we're doing here, or what we do subconsciously, is we try and condense all of these different measured values, m1, m2, ... all the way up to mn, into a single value representative of the measurement we want. There's going to be some spread in it. They're not all going to agree. But what are we actually doing with this? Well, you can view it as a system of equations, but you're solving for one value with however many measurements you've taken. So for n measurements, you're going to have n minus 1 degrees of freedom following solving for this value. Now, what are we actually doing when taking the measurement? I've had a lot of people subconsciously take an average, but they can't tell me why they're taking an average. So does anyone want to take a crack at what taking an average actually means? And I would appreciate it if we got some interaction from the crowd here. You're all blank staring at me. Ivan.
Statistically assume that you create a model where theoretically, if all of those values were evenly distributed among each other, among every single measure, what value would you get on average?
On average. So you're using the word average, on average, in the definition of average. It's a bit recursive. You have a...
I would say averages are talking for unknown uncertainties.
Okay, unknown uncertainties, that's a good one, yes. We can get rid of a lot of those uncertainties by measuring. Did you have one, Elia?
Generalization.
A generalization of the pool of data. Okay, these are all actually pretty good definitions. Ivan, you want to give it another shot? Yeah.
What it means is that if theoretically we would get the exact same grade, what would we see? So it basically means evenly distributing.
Evenly distributing, that's a good one, that's a good one. And actually you can see that from the formulation here. You're summing up everything that you have and then you're dividing it equally among all the n terms that you have. So I drew this in MS Paint. Please don't hate me. And it's green just so it stands out against the blue background. So what we're doing here, well, I have green water. Let's say it's from the swamp out in front of the university there. And the vials, they have a varied amount of water in them. What we're doing when we take the average is we're taking every single one of those vials and we're dumping it into a tub. That's what this sum is. We're summing all that up. Then what we're doing is we're saying, well, for a lot of measurements, we can attribute the same amount of green swamp water to each vial. And that is shown by this actually very pale orange line here. So what we're really doing when we average something is we're looking at the long-term behavior of our measurement. Because the average doesn't tell you anything about how poorly the spread of water is. It tells you nothing about that. But what it tells you is, well, if you do this enough times, you're going to get about this number. In fact, so in the long run, we can attribute this roughly the same volume to each vial of water. And so it's long-term behavior. That is what we do when we average something. Because you can take one measurement, call it your average, and you're right. You probably shouldn't do that. So, what about the spread? You all know the answer. I'm going to bring up standard deviation. It's in the bloody title. But the answer is why. Or the question should be why. Why standard deviation? Why is it the way it is? So you've heard of standard deviation. You've seen this. Sigma squared, sigma for standard deviation, mu for mean. Greek letters are usually put in with some level of reason. This is called variance, and this is called standard deviation. And I want to ask, why does it look like this? Because this is not, for two big reasons, not the average distance to the mean for your measurements. What are the two reasons? Well, let's first look at the obvious one. For sigma here, square root n on the bottom. We had just n on the bottom for our average. So already that's a little odd. Next up, we have square root of the sum of difference of squares, which you might be tempted to look at as the average distance to the mean, but it's not. It's more akin to Pythagorean theorem, because if you wanted to just absolute value these numbers, you would put the square root inside the summation rather than taking it outside the summation. So really, this is a very odd formula to be introduced. It's not very intuitive. So I'm going to talk about the reasons why it looks like this. Number one, squaring the offset really punishes outliers that are further from the mean. So if you double the spread of your data set, you get a lot more variation, at least in this measurement. So what that means is that if you are very poor in your collection of data, that number is going to reflect it. The second, which is a bit hand-wavy, is that this standard deviation definition ties into the normal distribution very nicely. And the normal distribution ends up describing a lot of things, which I will not cover, at least in this lecture, or even in the one I have on distributions, because honestly, the normal distribution deserves its own dedicated lecture, in my opinion. The third one, we can actually talk about a bit more, is that this has a very nice identity related to it. And you can use that to figure out the means of some very odd, or the standard deviations of some very odd distributions that would be difficult to do directly. Because we can kind of talk about point 3, we're going to go talk about point 3 a bit more, and I'll show you with some math that actually took a long time to write. And so here's the proof. First, we want to talk a bit about expected values, just notation. Shouldn't be anything crazy here. The expected value of a function of x, we denote that with these little sidebars. So these guys. And all that we're doing is we're summing an outcome, xi, with the probability of that outcome occurring. So let's say you're gambling, right? Let's say you got the silly example, people say where you're at a school fair and they have the wheel of fortune, you win $5 with this probability, $3 with this probability, and you give the PAC or the parent committee $2,000 if you lose. What would you expect to get if you spun? That's what this is. So standard deck of cards, the expected value of getting a 4 of clubs from one draw is 1 over 52. 1 over 52 is the probability for each card, and there's only one value that you'd expect to get out of that deck. For the spade suite, 13, because there's 13 spades, each with 1 over 52 probability, and the probability of getting a red is 26 over 52 for the exact same reasons. So if the probability of each event is the exact same, for however many n events that you get this, so the sum of all the values, over however many values you have, which suspiciously looks like your mean or your average. And that's because it is your average. This is what you're actually doing when you're looking at the average. So the expected value of x, so let's say f of x is just x. Expected value of x is in fact the mean. Okay, so just the big idea here is the notation of what we're looking at, which is these sidebars are expectation values. What it means, if every probability is the same, just sum it up, divide by n. So we're going to determine this very unique, very powerful identity associated with the variance definition. So we're going to start with our definition of variance. Sigma squared is the sum of xi subtract mu squared over n, which is the expected value of, do I write it out here? No, I don't. But that's the expected value of x minus mu. Same thing. So we're going to extend this, this summation here because we can. So we're going to expand this, this power of 2. We're going to get the first term squared, and because it's a subtraction, minus 2 times the first term, second term, plus the second, or the second term squared. And then, of course, each of those is a sum just because we had the summation symbol there. And if you're confused at any point while I'm doing the mathematics, please raise your hand. Because contrary to popular belief, I'm not here to make you suffer. I'm actually here to teach you guys. So if you don't understand the mathematics, come talk to me after class, send me an email. Raise your hand. Okay, so this seems pretty good. This is just some algebra. And we can separate out this rational. And then we can rewrite this one as the expectation value of xi squared. That makes sense, right? We talked about expectation values here. It's the sum of xi squared over n. So it makes sense that we can describe that as the expectation value of xi squared. Next up here is we have this summation here with 2xi mu over n. The mu we can take out because it is not indexed in our summation. So there's going to be a mu for every single term we can factor out through multiplication. The 2, same thing. So what we are left with is the sum of xi over n, which is mu, exactly. So that's where we get minus 2 mu squared. And then, of course, same thing happens here, where this is just the expectation value of mu squared. We can factor that out. Expectation value of 1 summed n times is going to be n. We're going to cancel out that n there, and we're left with mu squared, because this is not indexed, and I'll talk a bit more about that later on. So there we go. And we can combine those two mu terms, the minus 2 and the plus 1, into a single mu term. And what we can say that mu is, if we're looking at the expectation value notation, is in fact this, which is the expectation value of xi squared, subtracted the expectation value of xi, comma, squared, which is very, very handy when you need to figure out the standard deviation of something like the Poisson distribution. It's very annoying to do it by definition. Using this instead is very, very powerful. Next thing we want to talk about, oh, do you want to go back? You good? Okay. Getting confused. Again, if you want me to go back, just say so. Covariance. So that was variance, or sigma squared. I don't know if they've ever taught you guys covariance. Have they ever taught you guys covariance in stats? Shaking heads, shaking heads. Okay, so I'll take some time to go through this one then and make sure that everyone gets it. So this is our variance definition, right? We've all seen this. We've all had to deal with this in statistics in second year. This here is covariance. What's the difference? It's a spot the difference game. Can anyone tell me what is different between these two? And I'd be a bit worried if nobody answers. Ivan, please.
First of all, the bottom one has y.
Bottom one has y. Okay, so we're looking at two variables. Anything else somebody notices? I mean, yeah, we have, instead of a square, we have a second factor that is in terms of y. It's the same thing, same form, but now it's just in terms of variable y. So covariance is looking at two variables. Variance looks at a single variable. And from this point on, I think I've forgotten what's on the slide, so I'm just going to wing it from here. All our variables must have the same number of measurements, the same number of entries. Why? Because they're all divided by the same number. If you take 5 y measurements and 10 x measurements, and you try and tell me what the covariance is between them, I'm going to not give you marks for whatever I was asking. Because they need to have the same denominator. That makes sense. That's a reasonable ask. And unlike variance, this can be negative. Why can it be negative? There is no squared term. So if you have a positive term here and a negative term here, it doesn't get squared. So it doesn't disappear. So covariance can be negative. In fact, this is why you use covariance in linear regression. Yes, Ivan? How would you take a square root if it's negative? That's a very, very good question. And the answer is you usually leave this as variance squared. Unless you want to get into complex math, which I don't think they usually touch in linear regression, although it's been a while since I've touched that by hand. Okay, so let's look at some examples here, and let's play a little game. You guys tell me whether you think the plot I show has positive, negative, or no covariance. So first one here, I don't know if it's visible, that's good enough. We have a blue and orange sinusoid. The green line is the mean for both of them. What would you expect this to have, positive or negative covariance? And we can look at our definition here to see that it's positive when both are above their respective means, negative when one is above the mean, one is below the mean, and 0 if there is absolutely 0 correlation between their position relative to their mean. So we have a blue line, an orange line, positive, negative covariance, 0 covariance. What are we thinking? Positive covariance. Anyone disagree with that, or does anyone agree with that? I see some people nodding their heads. That's good. Yes, this would have positive covariance. The functions are above their means in phase at the same time. So what about this one? I think it's fairly clear based on the previous example, but does anyone want to raise their hand and be brave for the rest of the class? Negative, exactly. And now what about this one? It's a bit tougher. I see some eyes glazing over. What are we thinking here? Get a hint? We're looking at the correlation between position of the function to its mean. Both of these have the same mean, but we're summing up all their points. So is there a correlation between these two plots, the blue line and the orangey red sinusoid? No correlation. What does that tell us? Our covariance is actually going to be about 0. So this is what covariance tells us. It tells us how different parameters are related to each other. Now you can imagine in error analysis, you can go, yes, the error on this calculated value is this. But if the values depend on each other, maybe there's interactions going on that you are not quite yet accounting for. And for these sort of reasons, this is why we use covariance when we're doing linear regression. Because what are you doing in linear regression? You're looking at the relationship between two variables. And if they're correlated, then they should have a covariance. And underlined here, because it's very important, independent data sets have 0 covariance. Are there any questions on this? If it's unclear, please speak up. No? Are we good to keep moving on? Okay. I'm not saying all that. You can read it. That's mostly for if you didn't come to class today or you didn't remember what I said. Statistics is very, very silly in that it has population and sample statistics. They're different, and you do have to treat them differently. These are your population formulas. We have very nice, very fancy Greek letters to describe our parameters. But these are only applicable in one scenario. And that is when you have every single data point in your set. You need to have every single data point in your set to confidently say, this is the formula I'm going to use. And for it to be true. You can use it. Nobody can tell you what to do. But if you want it to be true and correct, then yeah, you need to know all your population for this. So the question then becomes, if we don't get the entire population in our measurement, how do we describe the entire population from this smaller data set? And this is where we get into sample statistics, which is what you would most likely be doing in most scenarios. And they look a little different, and I'm very guilty of just using sigma when I mean S. But it all depends on context. You can call it sigma as long as you acknowledge that it's population or it's a sample. So what's the difference here? Well, let's look at the mean formulation. Is this any different from mu? any different from the definition of mu? No, it is not at all. So why is it different? Well, the real difference is under the hood, because instead of summing our xi over every single data point to ever exist in our set, we are looking at not that entire sum. We're looking at a portion of that sum. And the only way you could do that is by looking at the indices, where it goes to. And I was a bit lazy and didn't want to put the indices in all my summation terms. So x bar is the average estimate. It's an estimate of our mean. This is what you do when you take an average. S squared looks a little different. For one, this is not a Greek letter. This is, in fact, very much an English letter. Secondly, our mu is missing. It's replaced by x bar. Why is it replaced by x bar? Because if we're doing sample statistics, is there any way we can know the mean? The true mean? No, absolutely not. So we have to use x bar. And as a result from that, we have to put down an n-1 instead of an n. Now there's a couple ways of justifying this. If you want to look at a full proof, send me an email, because I'm not going over that. We don't have enough time. If you want to look at it on your own, this is called Bessel's correction, and it can be proved mathematically. The very hand-wavy explanation that I'm going to provide you all comes from degrees of freedom. Remember, after we solved our x bar system of equations, how many degrees of freedom were we left with? n-1. So if we're solving for x bar by dividing by n, and we need x bar to find s, how many degrees of freedom do we have? n-1 left to spend. So that's what we're going to put there. So that's a hand-wavy explanation. It's true, but it is hand-wavy. So if you want to see the full proof, send me an email or just talk to me after class. I feel like there was something else I want to talk about population statistics. Yeah, there was. Let's say we're looking at the system of equation context. We have the entire population. So I'm going to go back to this slide here. We have the entire population. We sum up. We solve our system of equation for mu. Why didn't that cost us a degree of freedom? Why is this still n? If by spending a degree of freedom, we had to put it as n-1 for our sample. It's really weird, but when you solve for mu, by definition, the value you have solved for is mu, which is a number that lies outside of your system of equations, which means you didn't spend a degree of freedom. It's very, very odd, and it's a weird justification, but that's how it works. So weird things you can do when you have population statistics, but usually in most cases, you will be having sample statistics. So know Bessel's correction, know that it exists, and make sure you understand that it's because you do not have the population mean. If you know the population mean, but you don't have all the population points, you can still probably use the population standard deviation, but you then can't call it sigma. You would still have to call it an estimate of. It's all about what you know and what you don't know when it comes to these. More things to address. Well, I already yapped about that. Okay, so I'm already getting ahead of myself. So this is called Bessel's correction. The proof requires a couple other proofs that I don't think you guys would know. Small ones, just expected value identities. But if you want to know them, again, I have them all written down somewhere. The other thing I want to talk about is the expectation value of x bar. What is the expectation value of x bar? Well, it's on the screen right now. It's x bar. But then right here on the other side of the screen, I have the expectation value of x bar is mu. Now either I'm delusional or there's a point I'm trying to make. And can anyone see the point that I'm trying to make here? It might not be clear, and that's okay. The point I'm trying to make is that x bar is a value. I take the expectation value of x bar, I will get that value. X bar I, however, is saying I have a set of x bars. I have a set of averages, and if those averages encompass our population, then the expectation value of that set is going to be mu. It's a subtle but very, very important distinction to make when you're looking at these expectation values. And from here on, it's going to get very, very mathematical. So we'll take a nice break here. If there's anything at all that you have doubts about, I very much encourage you to speak up, because if you're carrying doubts with you beyond this point, you're not going to have a fun time. So please ask questions if you are unsure about anything. I'm here to help. So we've learned our degrees of freedom. We've learned our mean, our average, our standard deviation, and why it looks like that. So you should be able to answer it if anyone asks you why it looks the way it does. We looked at a bit at expected values, the variance identity, which is very important if you want to do any more statistics, which I doubt, but if you have to, you should know it. Covariance, which they haven't taught, but now you have got a brief introduction to. And the importance and difference for population versus sample statistics. And there's all this formula garbage on the slides, which I just tossed on so that you guys could write a formula sheet nice and easily, if you want to. I don't think I'm ever going to have you guys calculate covariance or variance from the definition. If you have to use it, you'll just get it in the question. So are there any questions, any doubts, any concerns, any questions, queries? Nothing? Okay. I'm warning you. We move on from here. I will tell you what you need to know for your exam and what is put up there for enrichment material. And I want to preface it with, please do not get scared. It's a lot of math. But math, by definition, has to make sense. So if anything doesn't make sense, something is going wrong. But I am going to jump to a topic that you probably haven't seen, which is the multivariate Taylor expansion. When I show that definition, please do not be worried. Keep an open mind, stay calm, and I will describe and explain the components of the formula. Before we get to the multivariate, we need to talk about the actual Taylor series. That is not the Taylor series. That is, in fact, the Vandermonde matrix. Have any of you taken numerical methods? Numerical method which one's taken? The rest of you haven't. Okay, so we'll spend some time on this one. I think I should put the rest of the visuals on. Yeah, let's just put the visuals up. That way we can talk about it in depth. Where did I put my spatula here? Sorry, this is all I had. I don't actually have a laser pointer or a proper pointer, so we're rolling with the spatula. Okay, so what is the Vandermonde matrix? Well, it's this guy up here. Now, what does it mean? What is it trying to say? Well, as you can see, it is a very, very large system of equations that has a bunch of polynomials equal to a bunch of function points. Well, what happens is if you have 4 points here n equals 4, you can make a polynomial that describes this by setting up an appropriate system of equations with the right number of equations. So 4 equations for 4 unknowns. Now, if you have 4 equations, you have a constant term, a linear term, a quadratic term, and finally, a cubic term whose coefficients you can solve for. So the degree of your polynomial is n minus 1, where n is the number of data points that you have. So if you wanted to get really, really silly, you would take a lot of data points. And then what you would do is you would make a very, very poor numerical error, or very funny numerical error, depending on how you see it, which I wish I had a plot of up here, but I don't, where you make like an 80th degree polynomial to describe a function. And Does anyone want to take a guess at what those plots look like when you overfit a polynomial to a curve? They kind of look a little something like going up and down and 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 up and down. Because with 80 degrees in your polynomial, it can have a lot of peaks. So the reason Vandermonde isn't used a lot is because it does risk overfitting a curve. So in between your data points, you don't actually get a nice interpolation. You just get a bunch of crazy BS. So why do I have it up here if it has so many issues? Well, what happens in the limit as n approaches infinity? You have every single dx data point on your curve. There is no more physical room for that Vandermonde polynomial to overfit itself, to go crazy up and down and up and down. What happens? Well, if you have every single data point, you're solving for the function. The function itself. So in fact, this is where, or at least how I like to justify the Taylor series expansion, which is this right here. If you want a proof of why it looks like this, again, talk to me. I have it written down. What we're looking at here is we have a sum to infinity. The moment you take out that infinity, that becomes a tilde on top of the equal sign because it is no longer exact. It is instead an approximation. So the Taylor series, as I'm sure you know in Calc 1, you used it a lot to approximate functions. That's because it is actually used a lot to approximate functions in the real world. So how do we generalize this to multiple variables? It's a very tall order, and by tall order I mean it's a lot of terms to deal with. The algebra is just tedious. It's not hard, it's tedious. Now what's going to be terrifying is the formula that's about to come up here. I think it's on this slide. Yeah. So please don't get scared. Really what we're going to do here, I think it's on the next slide. Sorry, you guys are safe for now. We're describing our f of x as an infinite polynomial, infinite degrees. That's what that dot 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 means, and it's implied goes to infinity. Now, what we really want is to push this to multiple variables. So here we have an infinite polynomial in x, an infinite in y, an infinite in all the dot dot dots, and of course a unique infinite in the z. So we can do this for however many variables we want. If you are not convinced that a multivariate function can be described as a product of these polynomials, the multivariate Vandermonde matrix is a thing. And I can show you it. Again, if you want to see the math, I have it. It's a lot to go through in one lecture. So do you need to know the Taylor series for this course? No. Do you need to know the multivariate Taylor series for this course? No. Do you need to know what I'm going to prove with these series? Yes. So I will box it. So this is actually the multivariate Vandermonde matrix. You can order it in a couple different ways, but as you can see, we start getting 1, we get x, we get a y term, we get an xy term, we'll get an x squared, a y squared, an x squared y, and all that stuff. And it gets real big real fast. In fact, for a degree n polynomial, you have n plus 1 to the power of m terms, where m is the number of variables that you have. And that's the single dimension of the matrix. Remember, it's squared. So it gets really, really messy, really, really quick. And this is probably why they don't talk about it much, and why I'm not really going to do much other than show you why we can get what we get from it. I think this is the slide that has the formula on it. There we go. There it is. So that looks evil, frankly. Don't misunderstand me. I don't like working with that. It's very messy, but we can generalize our Taylor series expansion in multiple variables to this guy here, and let's take some time to break it down because it is a lot. It is a lot, don't get me wrong. Do you guys know what sigma means, right? Sigma for summation. You guys know what pi means? Pi for product, right? Greek letters make sense in math, math needs to make sense. So what are we looking at here? So here's our infinite sum of terms. And what we're looking at here is P1, P2, P3, which correspond to the power index of our variable. If we're at P1 equals 1, that means our x1 term is currently at its first power. In fact, we can see that here. So if we liken this to the original Taylor series expansion, we have our differential term and our polynomial term. So as you can see here, we have the product of all our polynomials at the given power. So that's sometimes x power 1, y power 0, x power 1, y power 2. And that's what this product here is saying. It's saying as we index through all the powers, we're just multiplying them all together for each variable, for m variables.
Why not just have that?
The powers need to be indexed. It's a really messy formula, but I remember I spent a lot of time getting this one together. Let's see here. So if it's indexed under the summation, there is a term for every power. So we're actually summing through the powers here, but we need to multiply through all the different powers as well. It's odd. And this is why I say it's messy. It's a really hard to understand formula when you have sums of products of products. It is very, very messy. So I will instead, down here later on, I will expand out the first couple terms, and I will show you which terms we're going to use in our proof. Up here, or down here, we have the product of all the differential terms and the factorials, which we had in our original Taylor series expansion. This is now just the product of them all. And up here, we have the differential, which is the sum of all pi for the given thing. So the reason that we have this summation here is because as pi changes, these terms do change. So if we have di x, di y, we have di squared f, not di f, because we've differentiated it twice. So you don't need to memorize this. Please don't memorize this. You're going to give yourself a bad time. But let's expand the first couple terms so that you guys can see what's actually happening here. These are the first order terms, first order differential terms. They are very nice. We like these. They are not messy. And we're going to do it in 3 variables for a proof, just so you can see that it does generalize. So we have di f at abc, di x with x minus a. We have di f evaluated at abc, di y for y minus b, and di f for di z with z minus c. Very simple, very nice. We like this. This doesn't give me a migraine. What does give me a migraine, and what will probably give you guys migraines, is the next terms. So these are the squared terms we have here, because we have p1, p2 equal 1. This sum up here goes to a value of 2, so we have 2 there. X minus a, y minus b. So now that's where this product term is coming in, and this product term is coming in. Same thing for y and z, same thing for z and x. Do we kind of starting to see how the formula starts to work, a bit of a pattern behind it? And then, of course, these are still the first order polynomial terms, but of course not the first order differential terms. The last first order polynomial term, oh yeah, and of course we have our constant term. The last first order polynomial term is di cubed, di x, di y, di z, of x minus a, y minus b, z minus c. So you can see it starts to become a product of all these Taylor expansion terms for different variables. I mean,
So we'll back up to the formula.
Yep.
Why is the summation the lower bound? It says P1, P2 up to Pn. Is that because you're considering that
whereabouts?
the lower bound of the summation?
Here?
No.
This one?
Yeah.
Yeah. So the zero term is for this guy here. So when the powers are 0, when the powers are 0, it is 0. Now, the reason it's confusing is because I have here P1, P2, P3, and I equals 1. This doesn't mean P equals 1. It means that P1 is put into here, and P1 starts at 0. That's why it gets messy, because now I have to index the power term for each variable. That's why it is so messy like this. So that's why it starts at 0, but all our product of m terms start at 1, because we start at x1, not x0. The distinction isn't clear still. See me after class, yes. Yes. That's where we get this constant term from, right? So whenever you do the Taylor expansion, you also get a constant term, right? So that's why the powers start at 0. I here in these is indexing the power for xi, the power for xi, all the way through x2, 3, 4, up to xm. That's why it goes from 1 to m, not 0 to infinity. So it's the value of the power that goes from 0 to infinity, but the index, we want to multiply all the different indices along. All right, because this is just saying, well, for whatever value of the power of x1, x2, x3 is, we're going to put in the differential term, and we're going to put in the factorial term. Just multiply them all together for every single variable we have up to xm. This is why I say you don't have to understand it. This thing's a mess. But what I want you guys to really get away from this is, 1, it exists. 2, these are the first terms in the expansion for 3 variables. Of course, you can generalize it, but that would just make me typing this out in LaTeX infinitely harder and longer. And I don't have infinite time, unfortunately. So we're going to use these terms, and we're going to start with the air propagation formulation. Now, actually, I'll go back really quick. What we do with the Taylor expansion when we don't have all the terms is we're approximating a function. Whatever function it is, we turn it to the Taylor series, we take a couple terms, and we get a usually pretty good approximation of our original function in a form that is sometimes more palatable to work with. Polynomials tend to be very nice when it comes to differentiation, for example. So this is why we're going to use it for the air propagation formulation. For brevity, we'll condense the notation. I was feeling very hopeful when I wrote this, and I was going to say, I will just put a ... into the bracket, and everyone will get to see that means, evaluated at the numbers ABC. And then I was writing out all the stuff, and I just decided to stop putting the ... in because I was lazy. So I was ambitious, but I have to address reality at some point. So we're going to start off with a variable, v for variable, and it has components x, y, and z. I think we define v here. No, we don't, not yet. So it's pretty hand-wavy, but very logical to say that the average value of v is going to be evaluated at the average values of its components. That kind of makes sense, right? Average resistance is 5 ohms, and average current is 1 amp. What's the average voltage? You just multiply your averages together. So that's what we're doing here. I don't think anyone has any issues with this, right? No, makes sense. I'm gonna have to speed up a little bit, actually. We can use this to approximate the function here. So I'm gonna have to speed up. We have about 20 minutes left, and there's an example I want to get through. Constant term, first order, truncate all the other terms in the ... You will see why, because it already gets messy with just these ones. This v moves over as a v bar to the other side. So we're left with all the first order terms in the truncation. We square this. Oh, it's looking an awful lot like standard deviation. So we have to square all that. And this is why we truncate terms, because that just becomes a mess. And I'm not writing that all out. And neither do you. It's a waste of my time. It's a waste of your time. we start off with that expansion of squares with the squared terms individually, right? X plus y squared is y squared plus x squared plus 2xy. So where do we get all those 2xy terms in? We get them here. So we get our partial derivative times polynomial term times 2. That's just your binomial expansion, right? Except there's just so many of them and it looks terrible because we have all the partial differentials that we need to evaluate and we have 3 of these terms. So yes, it looks yucky. When you actually get down to calculating it, it's really not that bad. You just have to stay calm and remember that it has to make sense. If we sum across all xi, yi, zi, and thus all vi, we can actually call this, so instead of it just being a function, we can actually call this the standard deviation, sorry, not the standard deviation, the variance, the sigma squared of v, which is the sum of all these yucky terms divided by n. So x, y, and z should have the same number of terms because they also have what we will see to be covariances. So we can simplify this. This is starting to look a lot like your error propagation formula terms. That's not a coincidence. So our squared terms, our x squared, y squared, they come into these. So standard deviation times partial squared. Or you can put the partial squared times variance. The real kicker comes from the next ones, which are, in fact, partial times 2 times covariance. Now, in your estimation of this function, covariance between your variables has suddenly appeared and become important. So you get this final form, which I took the time to label here. So you have your variance of your actual variable. And what you'll notice here is if I cut off here on, I'm pretty sure that's the error propagation formula that Dr. Liu taught you. This is the one I'm teaching you. It has the covariance terms. Because you should be aware that they exist. Where did they come from? From the Taylor expansion. By cutting them off, you're saying that there's no correlation between the variables. Now, by cutting the truncated terms off, what are we saying? We're saying that our function has no second derivative dependence, which is an assumption to, 1, make the math easier, but 2, in most cases, it doesn't actually cause too many issues between what you would estimate with them and what you would estimate without them. And in fact, because these guys can be negative, they can either punish your error or help your error. And if anyone can prove to me whether the variance can ever be negative or not, I will make a case to Dr. Liu to give you bonus marks. So, okay. If you want to include the truncated terms, you now know how to. You just have to do the math yourself. But if you're going to be doing that, use a computer, please. For your sake, it's a lot of time, it's a lot of effort, and there's numerical methods for estimating this error that don't rely on this formula. This formula is good for hand calculations. That's why we truncated the terms, so that we would have nice covariance and variance substitutions coming up. So, okay. What else do I yap about? Everything that I yapped about, actually. They'll have to have the same sample size. All these V brackets are evaluated at the means, which I said earlier, I got lazy and didn't want to write ... And this formula can be generalized for more than 3 variables. It can be generalized for 1 or 2. The issue is that you get a lot more covariance terms exponentially as you add variables. So if you can find variables that don't have covariance, it's very good. And throughout this course, you probably, and I said probably here, may ignore the truncated terms and covariance. I can tell you with absolute certainty, and pay attention because this is on your exam, that you may ignore the truncated terms because that is just cruel if anyone had to touch them. However, the covariance terms, not so much. In fact, we're going to look at an example with the covariance terms, which is very, very much like the one I wrote for your midterm examination next class. So I would pay attention. And in fact, I can say the formula will be very similar, except it won't have powers of 2, it won't have addition, it won't have subtraction, and it won't have division, if you catch what I am saying. So this is our function. This is what we're going to use. And we are going to use the following data. We want to calculate f and its estimated standard deviation for whatever reason. So z bar is 3, x bar is 2, y bar is 1. I'm blocking it. Here's your sigmas, so those are your variances. And you have covariance terms that you must now account for. So we're going to do it without covariance first, and then we're going to do it with covariance and see how it changes our answer. Just to really highlight my point. So last slide was quite messy. Graphic design is not my passion, so I'm going to try and make a workspace here. Please don't hate me. Again, I'm not a graphic designer. So we have all our given data here, and we're going to work in this lovely, lovely space here. So please try to follow along. There's about 15 minutes left in class. So I will try and time it nicely. First things first, we know we want to evaluate our partial terms because we're going to have the partial of e, the partial of with x, with y, with z, and we have to use them in all our other terms. So what are they? Well, when we differentiate with respect to x, we're going to get 2x. These are constants. They go to 0. 2 times x bar, because it's evaluated at the average, is 2 times 2, which is on the screen. I hope everybody can do this. This is 2 times 2 is 4. Df dy is just z. Why is it just z? Because it goes to 0. Partial with y gets rid of the y term with a constant value z, constant because it's partial differential. And so that's just z. Z is 3. Z bar is 3 because we need to evaluate at our average. Same thing, we do it for df dz, and that's just y, which is 1. Lovely stuff. Next up, we kind of want to evaluate these terms, just so we can get the standard variance part of the formulation out of the way. So we can see here, by squaring that, we get the variance, and we get the partial squared. So let's look at what that looks like for x. Well, that's 4 squared times our, whatchamacallit, variance, which is 0.1. What's 4 squared times 0.1? It's 16. 16 times 0.1 is 1.6. That makes sense. That's not too bad. What about the next one? 3 squared times 0.15. Makes sense. That's 1.35. And finally, for z, what we're going to see is that it looks to be 0.2. Are we all on the same page here? Okay. So we can find our sigma f for just variances. We're not putting the covariance in yet, because this will be a very similar process that I expect you to do on the exam, where you go through variance first, then you add covariance. So we're going to sum these all up, and we're going to get 1.775. I don't think I actually ever calculated f in here. Oops. Oh well. That one's not hard. You just plug and play. It's the sigma that I'm really concerned with you guys being able to calculate. So 1.6, 1.35, 0.2, square root that all, you get 1.775. Does this make sense? This is what you've been doing with Dr. Liu. So up until this point, nothing different than what you've been expected to do already. Now, what about covariance? Let's look at the covariance terms. First, we have 2 times the df dy, or df dz, times the yz covariance, which here is 0.07. This is 1, this is 3, this is 2. I double check this. If you do find a mistake, though, I will try and get you something for that. But if there's no mistakes, I'm sorry, you're out of luck. This is about 0.42. Okay, so that's actually our covariance term for y and z, which is this one. So That's not bad. We're just plugging and playing with the values. And it's not bad because I'm not going to make you pull out a calculator, a statistical calculator, and calculate covariance and variance. Because that's a waste of my time to make the question. It's a waste of your time to do the question. And there's just no reason to do it, at least here. Hear people giggling, but it's true. They're laughing because it's true. Second one, partial x, partial y, covariance between x and y. This makes sense. We got this here, put into the 0.05, 4 times 3, which we got from the previous slide, and then, of course, the 2 there from our binomial expansion. 1.2, lovely. Now we're almost there. We just need one more term, which is this one, partial x, partial z. 2 times 4 times 1 times 0.08. Plug and play. That's all it is. You just have a couple more terms in your error propagation formula. How much does it change it by? Because if it doesn't change it by much, why are we doing it? Well, let's take a look. 3.15 is the sum of the previous term, so that's just the variances. So we left the variances here, covariance, 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 and all of a sudden our standard deviation is now 2.326. That's about 0.6 higher than what it was before. In fact, that is a 31% increase in your standard deviation from covariance. I would say that's pretty darn important. Now, those were some pretty weak covariances as well. What happens if your parameters are very, very much correlated? As you will see on your exam, it gets bad. It makes a very significant impact, at least relative to the original term. And even I actually think I still had small covariance in the question. But you can imagine, covariance is pretty high. Those terms get pretty big. And very, very important to not neglect.
Sorry, where did the 3.15?
3.15 comes from this slide. So 1.6 plus 1.35 plus 0.2, I think. Plus, it's just some of these up. Yeah. After that, we're adding the covariance terms. So what I've done here on this slide is it's the sum of all your variance terms and your covariance terms. So I've just evaluated each term individually as a number and I put it in here. If I got a number wrong, let me know. Because it was actually pretty late when I was doing this. So 3. Yeah, it's 1.775 squared. Yeah, because so what happened is when you evaluated your sigma without covariance, you just have the variance terms. So I didn't actually sum them up before square rooting. That's what the sum is before you square root. So if you square root 3.15 right now, you should get about 1.776.
So just to summarize this.
Yeah.
Take your partials, you add them up, you square root it.
Yep.
And then you square that value. And that's what you're putting into the next 3.15.
Pretty much. Or you could just take the, if I go back here, you could leave it as 1.6 plus 1.35 plus 0.2 instead of condensing it into 3.15. Right? Because if you add these 3 numbers up, it's 3.15. So instead of writing out all the variance terms again and again between the slides, I just decided I'm just going to put 3.15 in there because, again, putting these into LaTeX was actually a lot of work and time I didn't really have to spare, unfortunately, due to unforeseen technical issues. Question? Okay, just chilling. Okay, so yeah. So moral of the story is that covariance is actually very important. And if you fail to neglect it, or if you fail to include it and do neglect it, when it is in fact very, very important, as our dear professor, Dr. Pura would say, your bridge will collapse. Bridge collapse. Dr. Jenko would say, this is not engineering, this is you are an idiot, but that's Dr. Jenko, not me. Just include them. keep them in mind, and we'll talk a lot more about radiation statistical analysis next time I'm here, because I'm very unhappy that they are cutting environmental effects of radiation from you guys' program. It's a very good course. You get to go out into the fields, discover that there's too much tritium in the pond, do nothing about it, and then, but I can't get the field work into this class. What I can do is tell you how to determine if you have a statistically significant amount of radiation present. And that's pretty important. If somebody says, is this radioactive or not? And you as a nuclear engineer start scratching your head. That's going to be very embarrassing. So let's not have that happen. So I'll do that next class. And I think that is the end of the lecture. Thank you very much for all coming. If you have any other questions, talk to me, email me. Thank you for clapping. That was very kind of you.